We solved that half hour ago.
What is the 3 on the very end?
That,
Yes.
we need to figure out, in that final position, what is the displacement of the spring from its equilibrium spot?
Oh, okay.
So it's
Here to
that. Other questions? All right, solve for V. Just making sure we get the same answer as we had before. I'm thinking about 9.03 personally, but that's just the way my brain's working right now. Or hoping.
So that first kind of bit, the 1/2,
This?
that equals 417.92.
That last bit is 196. No, not that one. The one above.
This is 196.
Yes. And the bottom one is 58.77.
58.77?
Yes.
Yep.
And then I guess it's 2v squared. Now, because you moved it over, does the 417 have to be negative?
Wait, say that again?
Because you moved v over to the left.
Oh, I just,
I know you just do that.
basically I flipped the whole thing around. I'm gonna subtract these two
From the 417.
from both sides and just put whatever that's there. If you want to, bring this over to this side, then that would be a negative here.
So I got. Oh, wait. .03.
Which is what we had right here.
That is how math works.
Say it again?
That is how math works.
Yes.
Physics and math.
And if you did not get 9.03, you can either figure out what the mistake was, or assume you're right and everything else is wrong.
So that's just another version of how we did it again.
Yeah. Yeah. So if I said, what's the maximum speed? You have 3 choices.
Finally realized why pre-calc trig used to be a prereq. Because the last 3 or so units, vectors, dot products. And I'm like, wow, this would have helped in the beginning of the semester.
Somebody made that comment about 252 and Calc 3.
Oh,
It's not required, but it made more sense for him.
well, I'll be going into 251 hopefully with calc 1 and 2 in the middle.
Thanks. Questions?
We will be armed for physics.
So do realize that, let me do the exact same problem, except I'm gonna make it look different. I got a 4 kilogram mass hanging here. I pull it out 5 meters. So this is equilibrium here. I pull it out 5 meters. And I let go. What's the maximum speed?
9.03
Meters per second.
meters per second.
What's the maximum acceleration?
16.32.
60.
There we go. And it's the same problem.
You said hanging for this one, even though it's sideways? How you drew it?
It's the same, sorry. It's the same problem assuming that the spring has the same spring constant.
And the one you drew right now, it's supposed to be hanging, you just drew it sideways?
No, it's meant to be sideways, and let's go ahead and say that use of S equals use of K equals 0. Make it frictionless.
Okay.
Thank you, I should have been more specific. It is now the same problem. Assuming K 13.06 repeating newtons per meter. Happy now?
Yeah.
Okay. All right. Now I'm going to make it look very different, but it's only just a little bit different. Here we go.
Let's just go with how with just one problem, you can have 3 full pages of physics.
Just wait till you get to grad school.
Oh,
And then you realize you have 10 pages of an aside.
And it's all wrong.
It's possible.
You're definitely
Sometimes it was gibberish.
You're definitely getting emails from me when I get to grad school. I'm definitely getting, because my prof is horrible.
Maybe I'll be retired by then. And I'm just
Free Thanksgiving.
All right, so I now take a string attached to some point right here, a frictionless point. Angle the string and I attach a mass to it. And I pull it back and I let go. Now typically with vertically suspended things, the angle, you look at the angle with respect to the vertical instead of the horizontal. So what I want us to do is force diagram. What are the forces acting on the mass? I pull it back, I let go, and at that moment I let go. What are the forces involved? All right.
Tension for point of tension. That's it.
Yeah, okay. We are ignoring air resistance, of course. All right, what is the direction of acceleration?
To the right.
Circular.
That way? Is that what you meant by to the right?
Yeah. On the board, it would be the same way, so. Unless it's swinging in a circle.
Well, if you take mass on the end of the
Yeah.
string and you let go, which,
Just this way.
yeah, the acceleration is that way, not
Okay.
that way. Acceleration is that direction.
Okay.
Is that not like a curve though?
It will be, at that moment, it's like that. Then
Okay.
at this moment, it'll be that way, that.
So it'll end up being a curve.
It will be, but we only care about the snapshot in time.
Okay.
We don't care.
All right, because the acceleration is in that direction at that moment. Well, let's set up our coordinate system.
Up is positive.
Pardon?
Up is positive. I thought we were just establishing one.
Well, let's come up with a convenient coordinate system, because acceleration is in that direction. What should our coordinate system be to simplify the math as much as possible?
Make this way positive.
Up is this way.
Up is that way? I think, I only interpret that perhaps forcing it, you wanna make that a positive direction, we'll make that say I hat.
Yeah.
Yes.
And then J hat,
This.
okay.
Now, can we say that's perpendicular with the friction or no? Or not friction, for tension?
Say it again.
Can we make, or is that perpendicular with the tension?
That, this I should, this is perpendicular with the tension.
Okay.
Awesome. All right, so what do we need to break up?
Wait.
Yeah. All right, so part of the weight is down this way, part of the weight is that way. However you want to go about it. That angle there is theta. So this angle here would be what I refer to as theta prime. That angle there is theta. I have weight acting down. I know that this angle here is theta. Therefore, this angle here is theta. That's a lie. Weight's going down. This angle is theta. That angle there is also theta. So this side right here, the part that is in the I-hat direction, is going to be the weight sine of theta. The other one is going to be cosine. So we've taken our force diagram and we have tension going this way. We have, not drawn to scale, weight cosine of theta, weight sine of theta. It might be. Equations of motion. What are our two equations of motion?
Tension minus W cosine theta equals 0, or M. Okay.
You said MA?
I did say that.
We'll leave it there for now.
It should, is it not 0?
It is not.
Okay.
Then we're gonna have W sine theta equals MA.
All right, there's a problem written on the board now. You can either say that Jack made the mistake or Ibrahim made the mistake. Now officially, Jack would have been right since he went first and Ibrahim made the mistake. But either way, there's a confusion there. What is the confusion?
They can't both equal, I think.
Why not?
Because one we're moving in this direction,
Right.
not this this direction.
The one that's in this direction, what kind of acceleration is that?
No, nothing.
I assume that it will swing. I assume.
It will swing like that.
So it'll have centripetal acceleration.
This is centripetal acceleration. This is tangential acceleration.
Ha, you're wrong.
So centripetal, tangential. The tangential acceleration, that's the acceleration we were dealing with in the first couple chapters. Centripetal shows up in chapter 6. Somewhere around there.
Somewhere.
All right. I really don't care about the first equation. It's the second equation that I'm going to concentrate on. So I have mg sine of theta is equal to ma, and so my accelerations cancel out. Now I have an equation here with theta, which is an angular quantity, and acceleration, which is a linear quantity, so somehow I have to combine the two, merge them. So let's get it into angular terms. So if this distance here is L, what is the relationship between that tangential acceleration and angular acceleration?
LR, L times R, I think, or dot R.
What's R?
No, that's the same thing.
Your brain is cruising around, you're almost,
Is it L times omega? I think. For the angle.
what would be, all right, if that's L, what would be L times omega?
Mhm.
And what would be? Let's think about it from the unit point of view. If I do L times omega, I have, let's say, meters times radians per second, which would give me meters per second. L times omega,
Speed.
the V equals R omega. That's the relationship for speed, but I have acceleration there, so what's the relationship between acceleration and angular acceleration?
Does it use alpha?
And we'll use an alpha.
Alpha equals L times omega?
L times omega still would be meters per second.
Okay.
L over omega.
Cast omega from your head.
LO, same thing.
Look at the pattern here. Next level down,
V equals R.
not V.
Well, no.
We're looking for acceleration.
Okay.
A equals,
L.
okay, R alpha, in this case, R is L.
Oh.
So I have G sine theta is equal to R, sorry, L alpha. Now the solution is obvious. Now there's one other thing here that I ignored, and I traditionally ignore because I don't think about it until this point. There is actually a mistake here. It's not gonna require a huge rewrite. But when you release it, what is the direction of the angular acceleration?
You said angular acceleration?
Yes, the direction of the angular acceleration.
That's different from our centripetal acceleration?
Yes, centripetal acceleration is that way.
Would it be like
Right angle.
Oh.
Oh, to the board.
How'd you get that?
There's a little curve like this. Shove it in the board.
So, what's going, do you have something that's going this way?
No, it's going out from the board.
Okay, it's going out. When I let go, that thing is gonna be going like this, it's gonna swing that way.
Oh,
So my angular acceleration is out of the board. What about my angle? What's my initial angle?
We don't not have. We need to
If
do
zero is here, and then I pull it this way,
Negative. Yes, negative angle. If we think.
oh, okay, into the board. I think that's what you're going for, because if that's zero right there, and then I pull it this way. In other words, my acceleration, angular acceleration is in that direction, but my angle's in that direction. There's a minus sign that's missing.
The angle.
Wherever you wanna put it, just because, I generally would stick it over on that side, but I'll put it here, just because I got more room.
Is it the theta that's negative? Or is it just the
We didn't actually define the positive, we did define the positive direction. When we established I hat, J hat like that, K hat would be out of the board. So it is the angle that's negative.
Okay.
And sine of negative theta is the negative sine of theta. Let me write that one down. Sine of negative theta is equal to negative sine of theta. It is what is referred to as an odd function. Even functions, like cosine of negative theta is the same as cosine of theta. That's an even function.
What? Okay.
There are some shortcuts that, once you recognize if an equation, if a function is odd or even, there's some shortcuts that you can take in calculus. And also, personally, I didn't know what an odd even function is when I took the AP test in calculus. And so I live with that regret for the rest of my life. That's the worst thing I've ever done.
as far as worst thing goes, you're a saint.
There are two of us who took the AP calculus test, and after the multiple choice section, the moderator said, "Huh, you have 20 answers that are different." So I turned to her and I said, "Sorry, you missed them all." She actually ended up with a Morehead scholarship, so I assume I know which one of us got it wrong. All right, so now we have this. This is not particularly, that can't, probably not many of you are looking at this and going, okay, I can solve that. Remember Hooke's law. It'd be really nice if we could get it in some format of k delta x is equal to
Come here. No.
negative in A. If I can get it in some form like that, yeah, that would be great. But this pesky sign here is messing it up. I introduced to you the small angle approximation. This remember, all this was developed for computers, or a computer at that point was a person with doing it all by hand. If you look in radians, if you're dealing with radians, if theta is much less than 1, so the two less than symbols mean much less than, then the sine of theta is approximately equal to theta, which is approximately equal to tangent of theta. This again, theta, the units of theta is radians. Does not work if you're in degrees. If you plotted it out, can you see 3 lines on this?
Yes.
One of those lines is theta, that's the middle one, that's the red one. The one that curves down, the green one there that kind of curves down like that is sine, and the other one is tangent. Notice that there's a whole lot of overlap there in this first section here. When the theta is small, in this one, that's 0.2 right there where my finger is. So if theta is incredibly small, there's a lot of overlap between those 3. So if theta is small, then that becomes negative g theta, again, if theta is small, is equal to L alpha. It now is in the form that we have over here, because alpha is the slope of theta, just as A is the slope of the position.
So this is just the angular form
Yes.
of that equation.
Yeah, in a sense. So remember that omega was k over m, square root of k over m. But I don't have a k and the n here, but I do have L and G in its place, so instead of k, I have G. So omega for this pendulum is the square root of G over, and then the coefficient of acceleration over there is m, over here it's L. Excuse me. This is incredibly important, although you might not see it at the moment, but I can connect it to something that's